Good evening, everyone.
Oh, that's there.
And thank you for coming out tonight. 2 months ago, Andy emailed me and he said, "Do you have a speaker yet for May?" No, I don't. He said, "Well, have I got a guy for you?" And so I've had the great pleasure of meeting Peter Jedicke tonight. And we sent out Peter's bio out with our email last week, but just to sort of give you the highlights, this is a man who has devoted his life to education in both Fanshawe College as a teacher, but also in astronomy. And he has written books, he has written articles, and he has done a lot for education for our community. On a personal note, you came to Canada as a child and lived in Niagara Falls and attended Wesleyan High School, as my son did.
Really?
He did. And Western University, as my son did. So yes, perfect education. And James Morgan as well.
Ooh, 3 for 3.
So yes, so very much part of our community, but also not just astronomy. Not only in his spare time, and I have no idea how you do it. It's very interesting to see rowing, because that's time. Mercedes, you have an old baby at home, do you? How lovely. Chess, and most importantly, wine. So a very eclectic individual as well. So tonight we're going to learn about Jupiter and the moons, and I'm really looking forward to it. So for you, and thank you.
Thank you very much, Tracy. Thank you, Hamilton Center, for inviting me. Tracy, I think that was perhaps the most effusive introduction I can ever remember receiving. So wonderful, wonderful. Thank you. So it's a pleasure to be here, both as your guest and also on behalf of RASC London Center. London Center and Hamilton Center are close enough geographically that we have felt connected forever and a day. How's the microphone working out, Dan?
Yeah, seems, yeah.
And Andy asked me to choose the topic of Jupiter for today's presentation. And I gave this as an introductory presentation at the Hume Cronin Observatory last fall. So at the Hume Cronin Observatory, we have monthly during the school year, weekly in the summertime outreach events. And every now and then the university faculty have a gap to fill. They scrape the bottom of the barrel and they come up with me. So I gave this talk about Jupiter. And did the little Jupiter video play? Oh no, here it comes. There you go. An adventure with the planet Jupiter I chose for my title tonight. I'm not sure how old this video is, but it does give you a lovely sense of something approaching, coming into basically our living room, and that's where we're going to spend the evening. If you are new to astronomy, I will try and keep you in our thrall with what's up with Jupiter. If you are, on the other hand, an experienced observer or an experienced astronomer from the armchair of your comfortable living room, I hope that I will tell you a few things that you'll find exciting and maybe even hadn't heard before. Let's begin with the name, of course. Jupiter is the king of the planets. And this is fairly widely known, of course, that the name Jupiter comes from ancient mythology. And so Jupiter was the king of the gods in the Roman mythology. It was identified back in historical times with the Greek god, the king of the Greek gods, Zeus, namely. And this photo, I hope you all recognize this, because if you are not a Netflix member, you should join it once and watch the series called Chaos. It's about the gods, only it's in the modern day. And they're really, really getting confused about what's going on in our modern world, as you can well imagine. It's a hilarious series. And Jeff Goldblum, who's one of Hollywood's greatest, he can do anything, that guy. And he actually plays Jupiter, or Zeus, in the series. If we use the adjective, I want you to know the word Jovian because I might just say that once in a while and I'll forget to stop and explain it then. So I'm explaining it now. Jovian means related to Jupiter somehow. Of course, Jupiter has a prominent role in many science fiction themes and series and so on. This painting is not from the movie 2001: A Space Odyssey, but in the movie 2001: A Space Odyssey, you might recall the spaceship, which is drawn up by the artist in this painting. The spaceship was called Discovery, and the spaceship goes to Jupiter, and fun adventures happen. I deliberately chose a painting not directly from the movie, so that if you are sitting here right now and you're thinking about fond memories of having seen the movie 2001: A Space Odyssey, you won't be disappointed because there's no way I can just pick one thing out of the movie. So it's a painting that's just inspired by the movie. And if you are one of those rare individuals, I'm not even going to ask for a show of hands, but if you're one of those rare individuals who's never seen 2001: A Space Odyssey, I encourage you to go out and see it immediately. If you haven't seen it for more than 10 years, I encourage you to go out and see it immediately because it's now available in 4K. And it's spectacular. Anyway, that's not the only occurrence of Jupiter in science fiction, but it certainly gets the idea across. And if you have other examples of Jupiter in science fiction in your mind, share them afterwards. I could have a long list, and I didn't want to go there. All right, here we go. Beginners, basic facts about Jupiter. Everyone seems to know that there are planets going around the sun. Jupiter is one of those planets. It is, in fact, the fifth planet from the sun. The diagram that I've chosen here is oversimplified. And again, I did that deliberately. I didn't put in all the planets or anything like that. Jupiter's size, 140,000 kilometers across at its equator. That is about 2/3 of the distance between the Earth and the Moon. So if Jupiter were somehow squeezed in between the Earth and the Moon, it would nicely fill that spot, cause all kinds of other problems, of course. It is by far the largest planet. In fact, we could take 1,000 Earths by volume and squeeze them inside Jupiter. It's actually an easy stat to remember. 1,000 Earths fit in Jupiter, 1,000 Jupiters fit in the sun. It's a nice sort of way to keep those scales separate in your own mind. So you might think on the surface of it that if it's 1,000 times bigger than the Earth, it should be 1,000 times more massive, but it's not. It's made out of less massive materials, so its density is lower than the Earth's, and so it's only about 320 times as massive as the Earth, 320 times more massive than the Earth, and that's still quite considerable. So it's still a pretty hefty planet. It is the most massive planet in our solar system, the most massive object in the solar system, other than the sun, of course. So when we calculate out the average density, 1,400 kilograms per cubic meter, if you're interested in things like rocks, for instance, rocks typically have densities in the range of about 5,000 kilograms per cubic meter. Water has a density of 1,000 kilograms per cubic meter. So Jupiter on average is more dense than water, but it's quite a bit less than rocks. And again, that's an important thing to keep in mind in terms of scale. Even if you forget the numbers, keep the scale in mind. That's always something you want. As you may know, all the planets in the solar system are traveling in more or less the same plane. We call it the ecliptic, and it's defined by the Earth's orbit, since we're on the Earth. And Jupiter's orbit is only 3.1 degrees inclined to the ecliptic, and all of the major planets are fairly close to the ecliptic. So there's nothing unusual about that. You'd kind of expect that. Jupiter rotates fairly quickly in only 9.5 hours, reckoned by our clocks. And that's pretty fast. For such a large object to be spinning so quickly, it does lead to certain effects that you can perhaps imagine, or else you might ask your physics teacher if you want to know about that. It takes almost 12 Earth years to do its orbit around the sun. Of course, while it's moving, we're also moving. So we go around the Earth we go around the sun once in a year. In that time, Jupiter goes around the sun 1/12 of its entire path around, which means that in each year that we travel around, we then need to wait another month to catch up to Jupiter again. 1/12 of the next year. And again, that's an important thing to keep in mind in terms of scale and in terms of presenting yourself in the night sky with Jupiter's apparitions around. So if I take the almost 12 years and multiply that out, we have 4,333 Earth days for one Jupiter year. And that again is something like 4,333 days is more than 10 years, is 12 years. Kind of get that in your mind if you think about what have you been doing the last 4,333 days. If you keep a journal, as I do, then you should be able to go back and trace all those days in your life. And meanwhile, Jupiter's just been moseying its way around the solar system out there. But now let's divide it out. The Jovian year is 10,500 Jovian days. So if it were possible to imagine ourselves as part of Jupiter, we'd be spinning around. It would be 9.5 of our hours on our clock. I'm not sure what the Jovian folks would use as a clock for themselves. If they chose our pattern and divided their day into 24 equal time periods, they wouldn't be hours like our hours. Oh, okay, that's fine. Still, the ratios are important. We can calculate those out. 10,500 Jovian days in a Jovian year. And you could figure out what that does in terms of the turning with the hours if you want, and just do the multiplication. Now, Jupiter has a very shiny outer layer. It's more shiny than rock, more shiny than asteroids, but so it reflects 52% of the sunlight that hits it, part of the reason why it is so bright in our night sky. But at the same time, Jupiter is also emitting actually more energy than it receives from the sun because of the processes going on inside Jupiter. It's actually giving off a little bit of extra heat. Now, that doesn't make any difference to us observing it at night because it's not being emitted as visible light. The visible light that we see from Jupiter is pretty much 100% reflected, 52% of the sunlight that falls on Jupiter. That extra little bit energy that's coming out of Jupiter due to the processes inside Jupiter, that is not visible to our eyeballs. So it's still there. It's something to consider. Most folks think it's important to add up Jupiter's energy balance and realize that Jupiter's got a trade deficit of sending more out. Anyway, the travel of Jupiter in its orbit around the sun, as you can see the numbers there, it ranges from 741 million to 816 million kilometers away from the sun. And on the actual diagram, this is why I chose this diagram, you see the 600 million, which is about the average. A lot of folks get confused about averages in astronomy. The easiest way to calculate an average is to take the maximum and the minimum values of something that changes, add them up and divide by 2. That's the easiest thing. Now, that's not always mathematically the best idea because sometimes there are situations where the lower number dominates more than the upper and then you can't just divide by 2. But it's pretty easy in this case. As Jupiter travels around, it's moving at 13.4 kilometers per second in its orbit. If you're impressed by that, don't worry. The Earth and all the other planets are all moving in similar speeds. So there's nothing really unusual about that. And now that I have shown you all these statistics, I'm going to tell you there's going to be a test on Saturday. So make sure you remember all these numbers. All right, Jupiter's role in history is with the original planets. So there is no real discovery of Jupiter. Jupiter was known in ancient times. It's easily visible, as I hope you all know. And if you haven't seen it lately, you should look forward to it very soon. It's easily visible to the unaided eye. The idea is that Jupiter seems to wander among the background stars, which are almost permanently fixed. And so because it does that, it was considered in with the category of the classical planets that were known as wanderers among the background sky. There are 13 constellations, as you probably know, that make up the path of the sun going around, and all the planets more or less travel in that same band of those 13 constellations, which we call the zodiac. So Jupiter is one of those planets that travels along, more or less along the ecliptic through those constellations of the zodiac. And that's what you would want to know about. That's what you would want to remember if you get to be a Jupiter observer and do so on an ongoing basis. Well, all right. It would be interesting philosophically and historically if we could spend some time talking about how human beings realized what was special about these wandering planets. And of course, we now take it for granted. And in fact, I worry that even folks who, well, at any stage of astronomy, folks tend to take it for granted that this is somehow obvious. And it's very difficult for us to imagine what it might have been like thousands of years ago for otherwise perfectly average, intelligent human beings to try and not know what was going on out there, not know that Jupiter was a planet, not know that the Earth was another planet. So, in fact, Jupiter could only be seen as a bright dot. They didn't have any real clue about size or whatever kind of wonderful pictures might have existed back then. They just didn't know that. It was just something, and the process of realizing that is, if anything, is more interesting than just a discovery story. So while Jupiter doesn't have a discovery story, it does have an incredible part to play in the development of our human experience among the cosmos. If you're interested in looking for Jupiter, as you know, it generally is a thing you do every year. In your run up to summer observing, you probably think about where the planets are. Here's a finder chart for Jupiter for this summer. You can see that it started over there on the right with a bit of retrograde motion around the beginning of the year. And since then, it's been moving to the left. Now, of course, be careful if you're a beginner to astronomy, and you know the person at the front of the room says it's moving to the left. You always have to be a little careful what that means, because on a given night, Jupiter will move to the right and set in the western sky. But if you looked at it every night and drew its position on a map every night, overlooking the fact that it's setting in the west every night, you would notice it moving to the left across the background sky. And so there are the background stars. And if you're looking for some sort of signposts to get you nearer there, then what you do is look for the constellations Orion below the ecliptic and Auriga above the ecliptic. You see the bright star Aldebaran there to the right. At the beginning of the year, it would have been a real nice convenience to see Jupiter near Aldebaran. Now with Jupiter moving off to the left, Jupiter is getting farther and farther away from Aldebaran. And as we go through the summer, you can see it's moving through the southern portion of the constellation Gemini and getting farther and farther away from Aldebaran. Aldebaran is not the only bright star in here, but I just circled it simply because it kind of gives us a sense of perspective on this season of the year right here. So when it comes to finding Jupiter in the sky, I wish you great joy and happiness doing that throughout the course of the summer. And it's something you can do every year. Jupiter is almost always visible for at least part of every year, and that makes a great ongoing project. If you want to know more about these sorts of things and follow up on them on your own, the best resource of all, of course, is our own Observer's Handbook. When I give a presentation like this to a non-RASC club, of course, I have to go a lengthy explanation of who the RASC is and the kind of thing. There it is right there. There's our handbook. Are we selling any tonight?
No, but this one is available to borrow.
There you go. Yeah, and there you go. So anyway, Jupiter's their little symbols there in the top left give you a sense of scale for measuring angles across the sky with your hand. Now, honestly, I've never really bothered to do that. I just don't feel comfortable trying to look one thing relative to another in the night sky. It's just not something I've ever made an effort to do, but lots of folks will use these little tricks to tell what 1 degree is, 5 degree, 10 degree, 15 degree, 25 degrees across the sky. Jupiter's most recent opposition was at the end of last year. And at the bottom down there, you see, in fact, the next opposition is until the beginning of next year. So this is one of those rare years, once every 12 or 13 years, where in fact we don't get an opposition of Jupiter during our calendar year. Not that anybody cares, because Jupiter's just going to keep on moving. And if there's no opposition, the folks on Jupiter are just not going to make any notice of that. But indeed, if you're being introduced to the topic of oppositions, I again repeated this little diagram down here, which actually shows the moment of opposition. So opposition means that you've got the Earth in between Jupiter and the Sun. Now, it's always a little more complicated than that, so there isn't a straight line with Earth dead on that straight line. But if you drew a straight line from Jupiter to the Sun and waited for the Earth to come more or less close to crossing that line, that's where opposition is. It is opposite the Sun in the sky. So when it's noon, the Sun is directly up over somewhere on our meridian. Jupiter is down below on the other side of the Earth, more or less opposite. And similarly, on that same day, but 12 hours later at night, the Sun will be down there near the bottom somewhere, and Jupiter will be as high up in the sky as you'd expect to see it for that particular time. All of these things go into the big mix of being an observer and observing the planets and following the planets along from month to month.
Does the gravity of Jupiter affect Earth at this time?
So gravity can, of course, be calculated. Norm is asking about whether Jupiter's gravity affects the Earth. The short answer is, of course, it has to. We could calculate it out, however, and the strength of the gravitational force that we might experience here due to the presence of Jupiter 600 million kilometers away is minuscule, is extremely tiny. Now, that doesn't mean it's zero, but you would not expect to find any practical effects of this. And if you are, like I am, a person who doesn't like astrology, and folks talk about astrology and the influence of the planets, you can use Carl Sagan's description and say that, in fact, Jupiter's gravity has more effect on us than its astrological position does, which essentially means none. And that's exactly what Carl Sagan or any astronomer who doesn't like astrology is really trying to say. So the really interesting, the sort of most important event, the Stanley Cup of Jupiter's history occurred in the year 1610 when this lovely scientist, Galileo Galilei, whose portrait hangs in the Uffizi in Florence, when he looked through his little telescope, which basically was like the center out of a paper towel, a rolled paper towel. That's about all he had. And very hard to look through. If you've seen one of the many reproductions of Galileo's telescope, it's pretty amazing that he saw anything. But anyway, the night that he looked at Jupiter can, in no uncertain terms, someone's turned their monitor on. It's definitely not everyone there. But maybe you can monitor the list of participants and see who's got their mic unmuted. So that's not. I'm pretty sure it's not that one.
Yeah.
That's false. It's definitely not this one.
We're just sharing a video on that one.
Yeah, this one's got its audio.
Muted.
Yeah, there.
And no one else is unmuted.
Somebody threw with their cell phone. Could there be someone else with the cell phone on? Oh, has that solved it?
Yes.
Anyway. There's a cool video on YouTube that has something about feedback. All right, so what Galileo did, maybe could it be speakers even?
I don't think so, because you've been standing there the whole time.
It's true, I haven't done anything different. I'll stand further away. The Galileo contributed a lot to what we would, without any hesitation, call the beginning of modern science. And one of the contributions that he made was to invent the telescope. And perhaps even more important than just inventing the telescope, he turned it on the sky and looked at Jupiter, and his was that it all along? I don't think so. We had that off.
If the speakers.
Because I wasn't here.
If
I like that.
Peter, if the speakers were on,
They were.
it could have been on, yes.
Okay. Let's hope that solves the problem. Anyway, so and Galileo also made contributions to basic physics, things that you would study now if you were a high school student in grade 11 physics, third year in high school. And the book that he wrote called Dialogue Concerning the Two World Systems is a really neat book. He wrote it in Italian, so I haven't read it in the original, but I have read the English translation. And it's really kind of neat because it's actually not a dialogue, it's actually got three voices. And they go back and forth and they kind of joke with each other and they kind of try to set up hard questions for each other to answer about what the world is actually like. And if you read that, it's entertaining, but it also gives you a sense of perspective on how we, as human beings, as we like to think we're educated folks, how we think of the way the world is around us. Things like the Earth going around the sun, which is one of the classic things that Galileo gets credit for. But anyway, when he took his little tiny telescope and looked at Jupiter, the thing that he saw was
Plug the device momentarily, plug it back in. Back in. Should be green.
maybe if I. Okay. He saw that Jupiter has little buddies beside it. And these little buddies, of course, an experienced astronomer knows right away that these little buddies are Jupiter's 4 largest moons. We call them the Galilean moons because of Galileo's discovery on that night in 1609 or 1610. And he noticed within a day or two that these 4 little buddies are moving back and forth. This is the first time in the history of human thinking and human experience of the reality around us that anyone had ever seen anything that they could clearly identify as not going around us. We are not the center of, well, nowadays we would say we're not really the center of anything. But in those days, to be able to say that we're not the center of the world, the center of the universe, the center of everything, that was a sensation. And upset folks' ideas right down to their core. And, we live in a time right now, the last few years, where some of our really kind of fundamental things about how our world is put together, we do end up challenging them. And it just begins to give us a sensation of what it must have felt like to be an educated person in Europe in the beginning of the 17th century when Galileo made this discovery. It's pretty crazy. Anyway, that's a nice photo of the 4 moons of Jupiter. Of course, you don't always see all 4 of them because some of them can be in front of or behind the planet. You shouldn't be able to see them with your unaided eye unless you have extremely sharp vision. In my experience, I know 2 persons who claim that they can see the moons of Jupiter. And if and I don't think they're lying. I mean, the easy way to test it is to have them have Jupiter behind a building, and they're standing, away from the building. And if they can still see one of the moons next to it, then that at least that tells you they're seeing something. If you want to test it, more or less the easy way is you just ask them, well, do you see one on the left and 2 on the right, or what do you see? And then you look in the observer's handbook, and it'll tell you what's really there. Anyway, if you're one of those rare people, well, step to the head of the class. But the rest of us don't feel bad. You need a telescope to see the moons of Jupiter. Anyway, so we have this. First the business with the microphone, and then this. Do not want to start over, Ethan.
You hit the menu. Zoom menu, so,
It's in the Zoom menu?
yeah, it must be. The control. No, what I mean, no. You switch into the Zoom application.
No. Don't
See
want
if
to.
it moves out, try to move it,
No, it is not.
restart it. PowerPoint.
Yeah, okay, I can restart PowerPoint. And that means I have to restart the sharing and everything.
Sorry.
Second here. We're there. Okay, and of course, the better the telescope you have, the more beautiful Jupiter looks. The features shine, jump out at you with a better telescope. It's quite amazing to think that in our lifetimes, in recent decades, amateur astronomers, yourself, can get equipment that would have been considered pretty darn cool 20 or 40 years ago, and take a picture like this, which even the best professional observatory in the world 40 or 50 years ago couldn't possibly have taken. When the Hubble Space Telescope took photos of Jupiter in the early 1990s and folks marveled at how good it was, the picture that you're seeing right here is not, I mean, it compares favorably with what the Hubble Space Telescope can do. So it's really pretty amazing to think what kind of possibilities we have these days. And this photo is taken by Damien Peach, who's one of the best known amateur photographers for astronomy. Lots and lots of
Because you went back to the Zoom menu, you switched into the Zoom app and took you out of PowerPoint.
But what can I not be in PowerPoint, Norm?
In PowerPoint.
Don't just look at you. Is it moving now?
No, maybe we'll see if
Back up,
having a
back up,
menu
just back
there.
up, see if it's not.
One of the things you can do if you're interested in Jupiter, or interested in participating in astronomy at the next level, from whatever level you're starting at, is to try doing your own drawings of things in the sky. A drawing of Jupiter might look like this. This is a drawing done by our London Center chief observer, Dale Armstrong. Some technique hints are there on the left to use a soft lead pencil, something like a 2B. Do this at the telescope. Don't try and remember it and go inside. Use a very, very dim white flashlight to illuminate your white card. I do know some folks who do it on a black card and use some kind of a white pencil of some kind. Never done it myself, so I'm not sure which better or worse. But make sure you always include the details of your observing, like what kind of telescope you're using, what time it is, what the scene is like, the date, and so on and so forth, the temperature. Make sure you include all those kinds of things. This can be a lifelong pursuit. You can make drawings of Jupiter and you will always feel like you're learning something and getting better and better at it through your lifetime. You will never ever feel that, oh, well, I drew a picture 5 years ago, it's gonna look the same. Well, it may look the same, but it'll look different to you. You'll always see a little more as you get better and better. These are the names of some of the most prominent features that folks look for on Jupiter. You'll notice that they kind of, they all have this sort of horizontal look to them. Belts, as we call them, or zones. And of course, the one that's really the most striking is this one here, called the Great Red Spot. And, you know, if you're an experienced astronomer, I'm sure you're thinking right now that I should say this, so I will for the benefit of everyone. These are the product of atmospheric phenomenon in the outer layers of Jupiter's atmosphere. The colors are due to different chemicals. We think of our world as having white, lovely white clouds. They're gray underneath because of the shadow. But basically, every cloud you've ever seen above you in the air here on Earth is a water droplet cloud. On Jupiter, there's a whole range of different chemical droplets, and they all have different colors. And if you knew what they were, you could kind of look at this and say, oh yes, there's a little more of this and a little less of that. So that's how complicated it can get. They also are moving. In Jupiter's 9.5-hour rotation around, you can follow these things and fairly quickly. Think about it, 9.5 hours of one whole trip around. So the great red spot goes from one side to another in half of that time, which is only basically less than 5 hours. You can do that in one night if you're under good conditions and you are watching what's going on. So there's plenty of opportunities for that. And of course, to actually get this thing to do what it's doing, you need to be able to take video pictures. And even 10 years ago, that was a big challenge. But now folks have some pretty wonderful, fancy equipment, and it's not unusual for folks to try and aspire to take videos that look as good as this. You know, when you look at the motion of those clouds, now I found this, and this is a really old animation. This goes back, I think, to the early 90s with Hubble Space Telescope, if I remember correctly. And what they've done is they've analyzed or taken the video and they've doctored it so that, in fact, the great red spot is more or less held in place. So everything's moving, but they've computer analyzed the images and held the great red spot in place. And so the animation shows the motion of the clouds on the actual upper cloud deck of Jupiter. And you can see how some of them are moving one way, some of them are moving the other way. And this picture it's very hard to see the actual features developing in a matter of an hour or something like that. But that is also something you can do. You can watch the actual clouds develop as they move one past another. Again, because they're made out of different chemicals, it's actually not that hard to follow them because they have different colors. The weather patterns that you have on Jupiter are, in fact, not really dissimilar from what we're used to here on the Earth. It's just that they're more complicated because they're different kinds of clouds, different layers of clouds, multiple layers of clouds. And we are, of course, seeing them from the outside. When you observe weather patterns as a human being on the Earth, you're observing them from underneath. On Jupiter, nobody is doing that, as far as you know. Right? And if you like chemistry, I made a list of some of the most common elements on the top and the actual molecules on the bottom right. I don't know. I loved chemistry when I was in high school, but I never really pursued it. So I can't tell you off the top of my head if phosphine has a certain color and different from ethane or acetylene or whatever. But if you're a chemist, you might actually know those things right off the top of your head. So here's a Voyager 1 photo of some of a fairly close-up photo of some of the cloud patterns that we see in Jupiter. Of course, inside Jupiter is another question. We've never seen inside Jupiter, but the astrophysicists and the chemistry experts, they have ways of calculating what they expect to have there down into Jupiter. We only see the upper cloud layers. The most important thing about describing what's inside Jupiter for someone like me giving a presentation is to try and get across the idea that there is in fact no solid surface. There's no place to actually sort of land on Jupiter. As you go down, you can see the top here of the diagram represents the outer layer, and this is going down. There's no place where you actually have a line of discontinuity. You know, for us, air has a density of about 1 kilogram per cubic meter, and rock, as I mentioned, has a density of about 5,000 kilograms per cubic meter. And where we stand, there's a boundary between 1 kilogram per cubic meter and then all of a sudden 5,000 kilograms. It jumps fairly suddenly. You don't moosh around unless you've got a mud puddle. That huge jump from 1 kilogram per cubic meter to 5,000 gives us the surface. At no place down into the interior of Jupiter is there such a boundary, is there such a line. This comes from a textbook, and you'll notice they're using grams per cubic centimeter instead of kilograms per cubic meter, but that just means they're off by 1,000. And by the way, over on the side here, there's the Earth to the same scale. So the Earth is that tiny little wedge down there, and Jupiter's much, much bigger. So the Earth could be, any kind of little chunk down there, anywhere you want. There are, of course, the obvious questions. What is the pressure? Atmospheric pressure. We're used to 1 atmosphere. You probably know that a little bit higher pressure means the weather's lovely, and a little bit lower pressure means that are we not sharing?
No, you're still sharing, just that when you go to the screen, they can see you.
Oh, yes, right, okay, yeah, and
see you on TV.
okay, that was good. Anyway, so the tiny little bits of pressure difference here on Earth make for differences in the weather. On Jupiter, of course, something similar would happen if you were able to kind of pick a spot and watch small changes. But going down from the outer layers down, you do get fairly significant increases in the pressure, just no sudden change from one level to the next. So you can see a bar is roughly an atmospheric pressure. So 2 bar would be twice what our weather patterns change from something about 0.9 to something about 1.1. So how much change is that? Not much. In Jupiter, you go down a certain ways and all of a sudden you're at 500,000 atmospheres of pressure. So it makes a big, big difference. And down at the bottom, 100 million bars of pressure. It's so thick, the air is so thick that it would be essentially solid. But it didn't get that way at one particular level. So it gets thicker and thicker and thicker as you go down further and further and further. And you choose when you're fed up. And you just say, I'm not doing this anymore. And that's the end of your exploration. So far, we've only ever sent, I think it's really only 1 spacecraft has ever done this. And that was the Galileo spacecraft. They dropped it into the atmosphere of Jupiter after its mission was finished. And, it reported on the conditions going down. And it made it, an interesting, scientifically interesting distance down, but not anywhere near the center. It just gave up the ghost. It was too much pressure and it gave up and it couldn't send data anymore. But anyway, it's up there somewhere. Maybe the Galactic Environmental Police are going to be after us for littering on the planet Jupiter. Stranger things have happened in life. Anyway, so that's the inside. Here's a cutaway diagram of the whole thing. Basically says the same thing as the previous slide, just visualize differently. If you find that you have an easier time getting it into your head by thinking of it as a ball or a globe with a chunk cut out of it to show that same structure that was in the previous slide, then more power to you. That's really good. It does also, I also wanted to mention for this slide that the slide shows that there are some rings around Jupiter. Same sort of process as Saturn's rings, but they're much more diffuse. They're not nearly so obvious. We don't see them with the small telescope. Anyway, lots there to see and learn about. But at this point, fire away.
Why is there an aurora?
Oh yes, of course. Aurora are a magnetic phenomenon. So the sun is sending out all these, electrons and things that have positive and negative charges. When they get to a magnetic field, they start doing interesting actions. And as they plunge down near the North Pole of the magnet, they encounter different atoms and molecules, and they give off light. And that's the same process that causes the aurora borealis here on Earth.
So there's a magnetic core.
Yes. Now, that's actually an interesting twist. Most folks think of magnets as being related to iron, something metallic. On the Earth, for instance, the strength of our magnetic field for our planet Earth arises because we have this core of molten iron, and in fact, the rotation of that core is what gives us an active magnetic field. Well, Jupiter doesn't really have an awful lot of iron. I mean, it probably has more iron than the whole Earth, but it's mixed in with so much other stuff that it doesn't dominate the situation on Jupiter the way iron dominates the situation at the core of the Earth. Instead, what you've got down at the middle, you'll notice the words It says metallic hydrogen. Now, you probably don't deal with hydrogen on an everyday basis anyway. So telling you that there's such a thing as metallic hydrogen probably doesn't really scare you that much. But if you put enough hydrogen under enough pressure, the atoms of hydrogen will behave the same way the atoms of iron do that make iron a metal. So in fact, it is a metal, but it's hydrogen under intense pressure. And that's what the core of Jupiter has. And it's turning. And it's bigger than the entire Earth. So it's a big, giant magnet. And that's exactly what gives it that. Now, it would take an expert in magnetic theory to stand here and explain to you whether one is stronger than the other or why, or how much it matters that it turns or this sort of thing. I can't do that for you, but those are the factors that are involved in that. And if you really like thinking about what's going on at the center of Jupiter, you should turn to my favorite comic strip, XKCD, Randall Munro. And believe it or not, this is, I just saw this today. I don't know if XKCD comes out every day or if I just wasn't paying attention, but a friend sent me this literally just this morning. And when I picked myself up off the floor laughing, I thought there are some really good theories about what might be at the core of Jupiter. And I promised that I would mention the flat earthers. So there you go. Maybe Jupiter doesn't have a core at all. Maybe Jupiter is just a flat disk. And the flat Earth folks are right about Jupiter. That would be a big surprise. Anyway, I love XKCD, I can recommend it. How do we know as much as we do about Jupiter? Well, obviously the telescope, the amateur astronomers get a large charge out of looking at Jupiter that way, but we have sent quite a few robotic spacecraft to Jupiter. And here's a list of them on the left. And this is the Juno spacecraft in the diagram there. Now, again, I'm probably safe in a room in an RASC center, but when I give a presentation about Jupiter to a public group that isn't necessarily all astronomers, I have to be sure to explain that there is no camera out in space taking pictures of the Juno spacecraft. There's no selfies of the Juno spacecraft. That is a diagram done by an artist, of course. And they're very clever, and it's very wonderful that they do that. But anyway, no human beings have been anywhere near Jupiter yet. Every time I give a presentation in a public audience about anything to do with any part of space, at the end of the presentation, a child comes up to me and asks me if I've been to that place that I was just talking about, whatever it is. So no, I've never been to Jupiter, and neither have you. And neither has anyone else. Don't listen to them if they claim they have. In fact, here's a rather striking alternative to the standard views of Jupiter that I've been showing. This is the polar region of Jupiter. The Juno spacecraft in the previous slide was put into a path going over the north and south poles of Jupiter instead of just over around the middle. That's the easy way to send a spacecraft to Jupiter. So that's one of the photographs that it took. And you can see how much more complicated the cloud patterns look. The weather patterns seem to be much more intricate near the poles. And again, an atmospheric dynamics expert might be able to explain why that actually happens. But the fact that it's like that is pretty neat. We, of course, with our telescopes, we don't get that. We don't get that perspective on things. We might look near the upper and lower edge of Jupiter through our telescope, but we're not going to see it that way just because we're not in the right spot. And the colors, of course, have been doctored by the computer for the benefit of the scientists studying one thing or another, whatever it was they were doing. So here are those 4 moons, all in one slide together, shown for scale. So the lower scale, the line across there, gives you a sense of where they are. Jupiter's size, and then to the same scale as Jupiter's size, Io is the first one, and then Europa, Ganymede, and Callisto, and you kind of get a sense of how far away they are from Jupiter in terms of the size of Jupiter. And then the upper group, the 4 photographs of the 4 moons, show you the relative sizes of one moon relative to another. So there they all are. And 5,000 kilometers is the marker there for the upper scale. I'm going to give you the numbers for each one as we go through. Here's the moon Io. It's spelled Io, but it's pronounced Io. And it's basically purely volcanic. the entire surface of Io is all one big puddle of volcanic lava, basically. And the reason is that tidal forces, the strength of gravity from Jupiter, has kind of massaged Io over the billions of years and kept warming it up. It just squeezes and squeezes all the time. So all of Io is essentially on a borderline between being more molten and being solid, and it keeps flipping back and forth. This stuff gets cycled up and down, and there you can see in the right-hand slide up there, you can actually see a plume on the edge of Io. The first photograph that was taken by the Voyager spacecraft back in 1981, I think it was, showed a plume like that. I don't know if that's the very photo, but you can just imagine how wonderfully surprised the scientists were when they saw that first photo. I mean, if there's a plume on the limb of Io, if they thought there were going to be volcanoes, then they must have thought they were going to be really, really lucky to happen to see one on the limb. But it's just that there's volcanoes all over, all the time. So in fact, it wasn't just luck, it was bound to happen, basically. And then you have some of the names there. I'm not really clear in my own mind how permanent the features are on the surface of Io. You know, it would be an easy enough thing to go into the research papers that they publish, and they analyze the photos and see them from time to time. But whenever I look at a photo, I just look at how pretty it is, and I don't really, doesn't twig with me that, oh, this one was taken in 1981 and this one was taken in 1996, and look at the difference between them. But you can do that sort of project if you're interested. All of the photographs, of course, are publicly available on one of the NASA websites. Europa, the second moon, is interesting because it's still close enough to Jupiter that the gravitational tidal forces keep it fairly warm. And it almost certainly, in fact, I think most scientists would say they are sure that it has a very, very deep layer of liquid water. So there's a rocky surface deep, deep down there, and then it's covered, the whole planet has got a big liquid ocean around it that may be, you know, maybe even hundreds of kilometers deep. So there's an awful lot of water. And then at the top, it's cold because it's facing outer space, and it freezes. So there's an ice crust around oceans of Europa. And one of the exciting byproducts or outcomes of that particular fact is that Europa would make a wonderful laboratory to send a spacecraft to study and kind of drill through the ice and see what's in the water underneath. And that is on the books. They would love to get a few $1 billion to make such a spacecraft. Ganymede is not really as exciting enough, you know, there's no water on it or anything like that, but it is a mix. It's made of ice with some rocks mixed in. It is, what's interesting about Ganymede is it's the largest moon in the solar system if you measure it from its surface, you know, out from the center to its surface. And Callisto, the fourth of the big ones, is more or less the same as Ganymede, except the other way around. It's made of rocks with ice mixed in. So what dominates? And this is a fairly typical story for objects, smaller bodies than the actual planets in the outer solar system. They're almost all a mix of rock and ice, with some being dominated by rock and some being dominated by ice, and that makes all the difference in terms of their behavior and so on. You can see the surface has a kind of a pockmarked look. I've never heard anything other than just that is caused by billions of years of meteors, asteroids, small rocks plunging into it and leaving pockmarks. And then they stay because it's not an icy surface or a volcanic surface to blot them out. All right, the next missions that are coming up, in fact, I mentioned the idea of making some kind of a spacecraft to investigate Europa, and that spacecraft is called the Jupiter Icy Moons Explorer, but it will move around a few times. It'll stop at a couple of, it won't stop, sorry, I shouldn't have said that. I misspoke, but it will move around and eventually go into orbit around Ganymede. So by talking about the icy moons, they're talking about studying those in some detail. And the instruments on the spacecraft are optimized for looking at the moons, not for looking at Jupiter itself. And that's just a matter of the scientific and engineering design. So it was launched, well, less than a year ago, in October of 24, and will arrive at Jupiter in 2030. How much support the scientists will have for analyzing the data and so on, you know, is up in the air now with the political situation and the scientific funding in the US, but it is on its way. The other moons of Jupiter make for a wonderful tiny stories. When I was a little boy, I learned that there were 12 moons around Jupiter, and that's the names of them there. And then in the 1970s, a couple more were discovered. And since then, we've got many more moons that have been added by very detailed surveys. And in fact, we have a Canadian connection. Brett Gladman and some other Canadian astronomers have been using photographs taken by the Canada-France Hawaii telescope. And we may have, dozens of additional moons that are around Jupiter. And probably somewhere there's a website that says today's count is this many. They don't all have the kind of names that we would remember, but gradually over time, the discoverers do propose names for them, and you can find a list of them. The Observer's Handbook would be a good place to start to look for information. Where all those smaller moons are, they're whipping around Jupiter fairly, in a variety of different orbits, all more or less circles or ellipses, some tilted more than others and so on. When you look at this, it's supposed to give you an idea of where those moons are going, but I always want to make sure I emphasize that you don't think that these moons are leaving blue lines behind them in space. Okay? If we just took a snapshot, even if the snapshot somehow magically could see the moons as small as they are, it would just be a bunch of speckled dots. You wouldn't see their paths. We've drawn that in for our benefit and to make fun of. Imagine what it might be like to be there. I've been really impressed over the last couple of years at how ChatGPT is improving, and now the free version of ChatGPT will actually let you generate fictional diagrams and images. So I asked it to draw me what Jupiter would look like from the surface of one of the moons. There it is. Pretty cool. Jupiter, of course, would dominate the sky from where the moons are. Probably wouldn't fill the whole sky, but you can figure that out pretty quickly with angles and subtending and so on. It would be quite an interesting thing to see. Now, some folks then asked about life on Jupiter. And I remember this picture. I didn't use ChatGPT. I actually got that from Time Life books back in the late 1960s. Carl Sagan and his colleague Salpeter, I cannot remember, Joseph Salpeter, they published a paper in which they analyzed I've already talked to you about it, the pressures and the densities of the atmospheric constituents from the top outside going down inside. And as the pressure and density increases, eventually it gets to incredibly extreme values, but it starts at 0 and goes to extreme values. I mean, somewhere in there must be a place where it would be comfortable for us. Or if you're a biologist and you're thinking, oh, I'm going to design a biological creature that needs twice as much atmosphere. Fine. Somewhere in Jupiter, there's twice as much atmosphere right there at that particular level. So Sagan and Salpeter suggested, this is back in the late 60s, early 60s even, that there might be the right conditions for life on Jupiter, that there might be critters that would actually float through the atmosphere, gobbling up the clouds and so on. And so I made up the poem. The lifestyle on Jupiter is exceedingly grand. They float in the clouds and never see land. The poem goes on. You can look me up on, no, you can't actually. Listen, all right. Now, the most exciting thing since Galileo actually looked at the moons of Jupiter, and back in 1610, that happened to Jupiter, was in our lifetimes. In 1984, comet Shoemaker-Levy 9 crashed into Jupiter. And this was a sensation. Astronomers were getting a chance to see something they'd never seen before. I hope you all remember it. But on the other hand, I am getting more and more accustomed now to giving presentations where folks were not born in 1994, and they're either hearing it for the first time from me, or at least I'm explaining it in greater detail than they've ever seen before. This photo is infrared light showing the remnants of the impacts of some of the parts of comet Shoemaker-Levy 9 measured in the infrared. The photograph was taken at Calar Alto Observatory in Spain. Wow, it was quite something. This is the discovery photograph. The actual pieces of film are, I can't remember where they are right now. But anyway, it was discovered in March of 1993. The name of the comet is officially Comet D, 1993 F2, and the D means dead. The D actually stands for disappeared. When a comet is found, studied, measured, and then gone, they give it a letter D to show, and it's gone. And of course, the Shoemaker and the Levy come from folks that many of you had the chance to meet. What happened with Comet Shoemaker-Levy 9 is that they figured that as the comet was coming through the solar system, it came close enough to Jupiter around 1970. I have heard different numbers, but I think 1970 is the consensus. And Jupiter's gravity captured it and swung it in an orbit around Jupiter then. And then on the 8th of July 1992, the comet passed close enough to Jupiter that the comet's internal strength was not enough, and the gravity of Jupiter ripped it apart into separate pieces, fragments as we call them. And from 1992 on, it started to loop around, and basically its fate was sealed. The comet was discovered in March of 1993. The pieces were already starting to spread out. 16th of July 93, it was at its last maximum distance from the planet Jupiter. 0.31 AU is something like 50 million kilometers, so it's still a fairly far piece away. You'll remember that the farthest of the moons was only a few million kilometers away, and that basically its fate was already sealed. And then the pieces floated around, and since it was discovered in March of 93, means we knew it was going to happen. So we had advance warning, which is extremely rare. And in astronomy, you have a really, really dramatic event, and you know ahead of time, and especially that you know ahead of time specifically when it's going to happen. How many of you are following T Corona Borealis? We know it's going to blow up. We just don't know when. You have to check every bloody night. Well, this one, we knew exactly when it was going to hit. This is where Comet Shoemaker-Levy 9 was discovered. This is Palomar Mountain in California. Its importance has maybe faded a little with all the other stories about great telescopes. But the big one in front there is, of course, the Big Eye, the 5-meter telescope. And in the yellow circle is the smaller telescope called the Little Eye. And there's that photo is David Levy in the middle, Carolyn Shoemaker on the left, and Gene Shoemaker on the right. So you have to drive up there to get to that telescope. And there, that's me and that's Diane and I standing next to the telescope. That's our rental car. We were there in 1994 in March, just a few months before the collision. The telescope was a Schmidt type of telescope. It was one of the first Schmidts built after Schmidt invented the design. And this telescope also is famous because the astrophysicist Fritz Zwicky used it to take the photographs, which allowed him to make the rough calculations that later then were realized that they were actually proving the existence of dark matter in the universe. So it's not just a planetary telescope, but it is a 45 centimeter camera. 45 centimeter, of course, meaning that that's how big the mirror was at the back. This is the telescope today. It's no longer in the dome, it's at the visitor center. I don't know when they moved it, but it's been there for a few years. So I'm going to tell just very quickly, since some of you are new and you may not have heard this fantastically amazing story. This is David Levy standing next to one of the pieces of equipment up there at the telescope. What they did was they had film. Film had to be round to fit into the telescope where the telescope had a receiver. And this is film, not glass plates, but actual film. And they had to be cut out of square pieces that the manufacturer, Kodak, would provide. And then in order to make it more sensitive, they would put it in an oven and bake it in the presence of hydrogen gas. And if I'm not mistaken, that is the oven where they bake these things. And so one night in March of 1993, they had cloudy, poor conditions, and they weren't sure if they should observe or not. But this is one of the things that makes a real crazy, diligent, perseverant observer what they are. And Levy insisted that they observe, even though the sky was far from perfect. And what he suggested was that they had some film that had been partially hurt. In other words, someone had opened the door while the film was sitting there, and the film was light struck. And they weren't really sure how good the film was going to be. And you wouldn't want to waste that film on a really good night when you're hoping to take really important photos. Instead, you count on serendipity. And they put the partially ruined film into the camera on this less than perfect night. And this is Carolyn Shoemaker at the Discovery instrument. This is called a stereo microscope. She takes two pieces of film, taken about 45 minutes apart, puts them on the stage there, looks through the binoculars, it's a microscope with two eyepieces, and she looks at those two pictures, and she sees this, and she turns and she says, it looks like a squash comet. Now, they were in the business of discovering asteroids and comets, so this got them really excited there in March, and they wondered what it was. It's a stereo pair, that's how this works. If you're good at doing stereo images, you might make this work for yourself. Right now, I blew these up as much as I could. Just have it in your two eyes and let your eyes kind of lazily sort of drift a little, and you may actually see the squashed comet jump either up or down against the background stars. That's and if you want to look at it later, maybe I can call it back up again a little later here as we go through
It's
these.
a pointer.
Sorry?
There's a pointer on that.
Yeah, well, pointing isn't going to help me to make it look like it's three-dimensional. I think everybody realized that's what it was, and that would really screw anybody up who happened to have it in 3D at the moment. All of a sudden, there's a red pointer there. If you can make it do that, if you can make your eyes do that, it's really kind of neat. And of course, it's useful in many different applications. There, the idea of having three-dimensional view of pictures, can be done in many different ways. This is just applying this to a really interesting astronomical technique. So right away, they called up this guy, Jim Scotty, who was observing at the Space Watch telescope in Arizona, a few hundred kilometers to the east of Palomar. And they said, Jim, we're not sure what this is, but here's the position of it. And Jim wasn't too busy. Jim's never too busy, gotta tell you that about Jim. He said, I'll take the picture. Took the picture, that's the picture he took. He said his jaw dropped to the floor when he saw it. It's a comet with a tail going off to the upper right. I'll do it just for one. That's the tail there. And then it's got wings going off this way. Never seen a comet do that before. Wow, they were excited. And a few months later, the Hubble Space Telescope took this photo of the various fragments. This picture is called the String of Pearls photo. One of the most romantic, wonderful touches of this story is that in the summertime, when the comet hit Jupiter and disappeared, and Carolyn was all disappointed because she thought she had lost her comet, Gene pulled out from his pocket a string of pearls and gave it to her as a gift. They do that. Anyway, we're not really 100% sure how big they were, but of course, a few 10 kilometers across, a few tens of kilometers is the general range of what we have. They were given letters, so A, B, C, D, blah, 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 across from one side to the other. And then as the fragments broke up a couple of them broke up before hitting the planet. And that, of course, was how they were followed over the span of about a week or so in July of 1994. This is a photo of Gene Shoemaker when he was a little bit younger. Out in the field, he was first a geologist. His interest in astronomy came from an interest in watching meteors and so on crash into rocks. So rocks was his specialty. And when the close approach was calculated for Comet Shoemaker Levy 9, and it turned out to be less than the size of Jupiter. Okay, so the close approach was less than, means it's going to be an impact. And Gene read the email, he said, we're going to see an impact. He had never dreamed that would happen in his lifetime. He studies impacts, had never seen one, of course, always saw just the byproduct of them. And so this, they had figured all this out on May 22nd in 1993. That happens to be David's birthday, and the group of the three of them were at Palomar again that month, that day, when they got the news, and of course they were all really excited. Oh well, now before the comet impacted, you might, if you're old enough, you might remember in the spring of 1993, there was an awful lot of speculation about what was going to happen, whether the different fragments would actually get into Jupiter, what would happen when they got there. Would the gravitational forces pull them apart into such tiny pieces that wouldn't really have any major impact at all, or what would really happen? And some folks, felt that it wouldn't really be all that exciting at all. But of course, you had the cartoonists and so on all got excited. Yoo-hoo, look at the camera. The Voyager 2 spacecraft was still out there in the solar system and still able to take pictures. The Galileo spacecraft was on its way to Jupiter and not in orbit around Jupiter yet. But it was a good thing, actually, because the Galileo spacecraft was on a kind of a looping path. And the first impacts were happening on the side of Jupiter and a little bit around the edge, so we couldn't actually see them directly. But the spacecraft could. So we were able to get images of the actual impacts from the spacecraft. That was really kind of a lucky thing there too. Paul Weissman, who works at the Jet Propulsion Laboratory in California, he was one of the spoil sports who said nothing would happen. You know, they would just go right in and be a cosmic fizzle. Of course, David Levy and the Shoemakers were hoping to be a little more dramatic than that, because otherwise everybody would blame them for nothing happening naturally. Time magazine had it on the cover. Maclean's magazine had David's face on the cover as being the discoverer of this wonderful scientific event. So here's a loop. Don't be confused. This is not multiple impacts. This is just one impact. I could only find this particular loop. It's a half-second video, and then it's just looping over and over and over again. So you just see one impact. The bright thing on the right is one of the moons, well, Io. The bright dot on the disk of Jupiter is the great red spot, but that flashing thing on the left that hits every half second, that is the impact of one of the fragments of the comet. And in fact, of course, as I said, it's actually happening just around, partially on the back side. So we're not seeing it directly. This is just the brightness splashing up above the limb. So it's such a big impact that the mushroom cloud, or whatever cloud or shape you want to call it, is actually going out past the limb so that we can actually pick it up in this little tiny video. Wow, pretty dramatic. Here are the photographs that were taken from the Hubble Space Telescope of the plume just on the limb there. And you can see that it's just over a span of just a few minutes. And when the astronomers were waiting for the data to come in from the Hubble Space Telescope showing this, of course, they were on the edge of their seats, wondering how much or how little they would see. The explosions, each individual explosion was more powerful than any of the nuclear weapons that human beings have ever tried to blow themselves up with. So it's a pretty big deal. Plume height of 3,000 kilometers. Temperature at the spot of the impact up in around 24,000 degrees. So it's really quite a big deal. And as I was saying, the impacts were on that back a little bit, but Jupiter turned so quickly that it wasn't long before the impact site would come around the front, and then you would see the results of the impact, the leftovers. And the leftovers were really, really quite dramatic. Here we are showing 4 photos. This is the photos from the Galileo spacecraft of one of the last impacts, the W impact. Remember, they went through the alphabet. And so you see how the 4 pictures taken one after another, about 2.5 seconds apart. And then afterwards, it took about, what says 11 minutes for the planet to rotate until you could actually see the impact site on the limb of the planet as viewed from Earth here. Wow, that was an exciting week. There's what they looked like. Big, huge blemishes like bruises on the surface on the upper cloud surfaces of Jupiter. The features were bigger than the Great Red Spot. And since the Great Red Spot is not hard to see with a telescope, that means you could see these impacts with a telescope. And if you remember, if you were there, it was really quite an exciting thing to look at Jupiter and see these impact sites one after another. And after a couple of days, they were still going around. There was a whole bunch of them that were big enough that they still lasted, and they lasted many, many weeks. And in fact, I'm told that if you look with instruments and so on, they can still see hints of where those impacts were, here now 30 years later. It's a pretty impressive thing. Those of you who are interested in the scientific details with the chemistry, of course, what happens is you auger in some kind of an object like a fragment going in there, and pushed out behind it then come all the chemicals. They gather in all that kinetic energy from the impact, and they spew it back and dredge up chemicals from deeper in the atmosphere. And of course, that was what really excited the scientists. They wanted to study those chemicals. It was like sending a probe into the atmosphere of Jupiter so they could learn about it. I like the fact that we have good memories of this today. This was a post that was on YouTube, a comment on YouTube just a few months ago. Some person, she was a little girl in 1994, She says it fundamentally changed her. That's really pretty good. I was already a wizened old adult and, it didn't affect me at all. But I can imagine if someone was a child, that this would be the kind of event that would inspire them. It was absolutely incredible. I love that. And you can do drawings and so on. Dale Armstrong, who I showed earlier, talked about his drawing skills as an observer. And this is one of his, two of his drawings during the impact week, showing the size of the impact blemishes on the planet Jupiter. We were able to see them, we were able to show them to the public with our telescopes. Folks who had no background in astronomy observing had no problem seeing these things when they were shown them. So it was really a spectacular opportunity for astronomers. The science, of course, was an amazing, exciting thing. This was the press conference at the Space Telescope Science Institute in Baltimore, right after the first impacts were happening. And in fact, it was during the press conference. The first impact actually happened while the press conference was going on. They timed it that way, of course. They did it on purpose. And they were waiting for an announcement to come from the basement where the astronomers were connected to this thing called the internet. They were receiving data that was coming in from various observatories around the world, as well as, of course, the Hubble Space Telescope images. And so Heidi Hammel, who basically made her fame out of this event, she was a young planetary scientist at the time, and now she's getting on in her career. And you can, so she came and brought this picture up that had been printed out from a laser printer down in the basement. You can see how happy Carolyn and David look. Jean is just staring with disbelief at the events that were going on, and everybody. It was a real media event, and of course it got an awful lot of attention. I'm not.
Prior to Shoemaker Levy 9, we had never had
on YouTube,
an
which I
opportunity
encourage you to watch. That's
to
Heidi Hammel,
watch an
not today, but
interplanetary
last year, I think.
impact
And
in our solar system.
Isn't that incredible? It's right in the middle. That's amazing. It's really awesome.
Video channel where he showed this.
Shoemaker Levy 9 was a comet that was
That was in the news. This is the cover of U.S. News and World Report. There was a constant stream of media requests for interviews and commentary and so on and so forth. David was a real trooper. He went to NASA headquarters one morning and he basically sat there in a small studio for like 4 hours doing 10-minute interviews with radio disc jockeys all across the country. They would say in his ear, you're not going to be talking to Jim in Denver. And David would say, hi, Jim, how's Denver? And then you'd hear Jim, the disc jockey, say, well, what was it like discovering this time? David would give the same answer he just gave to the previous 8 other folks who were interviewing him. But that's the way you have to do this. If you want to reach out to the public, you have to reach out to the public. There were star parties everywhere. I'm not sure what you had here in Hamilton Center, but in London Center, we were out at the Cronin Observatory with telescopes showing the blemishes on Jupiter. During the actual week in Washington, they had star parties at the United States Naval Observatory, which those of you who are politically active will know, is the home of the United States Vice President. And so the Vice President at the time was, anybody remember? Al Gore. And he actually came out and he actually was quite knowledgeable. So that's what the astronomer said. He was really thrilled to see the impact sites. NASA, which I don't know about today, but prior to 1994, NASA had a reputation of being rather, straight-laced and not doing a lot of, yelling and screaming. Nowadays, whenever there's a landing or something, they all clap. They didn't do that in those days. And they just turn to each other and say, everything's nominal, Jim. And that would be all they would say. Well, NASA started to change, and I think maybe this is when it changed. This was the welcome sign outside Goddard Space Flight Center. What a week! It was Comet, and it was the anniversary of Apollo 11. What was it, 25th anniversary of Apollo 11? And a space shuttle mission was taking place. For Jean and Carolyn and David, Henry Holt's the 4th person in this photo. He was an assistant observer at the Palomar telescope where they were quite often. It basically completely changed their lives for the next 3 years. They were constantly going and giving presentations around And it basically wrapped up with a scientific summary conference in Paris in 1996. Quite an exciting thing. And so